Almost live from National Semiconductor, the analog IC design and manufacturing capital of the world, it's the Bob Pease Show. Here's your host, Bob Pease.
Good morning. Here we are again. It's the Bob Pease Show with Paul Grohe and Pul Rako.
How you doing, Bob?
Our usual accomplices. And let's see, Paul, who's going to be our sponsor for today's show?
Today we have OK International, who is also, they own and run Metcal. So they make soldering stations, rework stations, dispensing stations, all kinds of great stuff, which ties into our lab segment about prototyping.
Very good. Let's see, our agenda today will end up with a discussion of soldering and desoldering techniques, and it's going to start out with some current source stuff. But before we do that, we're going to talk about previews of coming attractions at Bob Pease's website, which is www.national.com/rap. We're going to have more lectures going on. We're going to be in Japan by the time you've heard this, but we're also going to India, South Africa, Finland, and Kathmandu in May.
Are you going to go down to Antarctica while you're,
No, I'm not going
South
to
Africa, it's a little hot. They might get
No, we're not going.
30 guys.
Anyhow, the main topic of today's session is what's all this current stuff anyhow. And if you've been to the linear seminar, you've probably seen this if you weren't goofing off. But if you haven't been to our seminar, our linear application seminar, then you haven't seen it. So you might watch up. Because I like to measure things. And I like to measure current sources. And I think you get the idea that this thing back here was a current source. So we were playing games with costumes and setting up things. And the next thing we're going to talk about is the input section. Now, did I build this input section? Well, no, not exactly. That was what I was on the beautiful oil painting. What we have here is an LM399 Zener reference with a heater. It's got wonderful stability, but the tolerance is 3%, so you have to trim it. And you have resistor dividers with matched sets of resistors.
The heater's built into that part?
The heater is built into that part. It holds it at 87 degrees C.
Ooh, good stuff.
Yeah. So it has a very low TempCo. It has about 1 part per million per degree C, guaranteed max.
But this wouldn't be for a battery-operated product?
Not usually, no. You would not normally do this for a battery operator. Okay. And we put in an 18-volt supply because we're going to need a lot of output swing. We're going to have a 2-volt reference, 2 volts down from the 18-volt bus. Now, did I build this? No, not exactly. What did I build?
You're hanging the reference this way.
The reference is below the rail.
It's from ground up. It's
That's
from a point down under here.
Yeah, we don't want a 2-volt reference above ground. We want a 2-volt reference below the plus rail because we're going to make a current source working downward from the plus rail.
Oh, okay.
Now, when I show you this, I'm going to say, oh, this stuff is in blue. If it's in blue, you haven't seen this before. If it's in black, you've seen it. So I'm not going to talk about this and this and this because you've seen it, it's black. But the blue stuff I'm going to talk about because in the original circuit, we had a resistor from here to ground. So you run a milliampere or two, but when you change the 18-volt supply, this current would change a lot, which would hurt your accuracy. Now this circuit doesn't care so long as it gets a current. So we're going to make a current source that runs off the 7-volt Zener, and from the 7-volt Zener, we make another 7 volts, and we make a current of 1.4 milliamperes. We reflect the current, and it goes back up and runs constantly through the Zener.
So this is a little current source that's creates a reference voltage that's going to be used for the big current source.
Yeah, and this reference is also used to make the current source. Now, what if it doesn't start? If it doesn't start, that's another stable state. It won't start, and it'll never start. It'll sit there, and it'll never start. So if this current is 0 and this voltage is 0, there you are, 0. But by putting in a megohm here, I said, that ought to start it. So I put in a megohm, and it started. And I put a shunt across here, shorted it out, and it came back, and it started.
So that's just a little leakage current to
it's
get
a leakage current to get it to start.
But then the transistor takes over and does the modulation that has to happen.
Correct.
Okay.
Now, what else do we change? I put in a little trim pot here, just a tiny amount. 100 ohms here has about 1% of the voltage here with 10K matched resistors. 10K, 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 10K. This divider is very stable, very low TempCo, but I put in 100 ohms, 1% metal film. And then I put 5K across it. Now, what if I put in a 100 ohm pot? Well, the 100 ohm pot might have a lousy TempCo. and it would hurt the accuracy of this divider. But 100 ohms at 1% low tempo means this resistor has no effect, the pot has no effect, and we come up with 2.1 volts below the plus rail.
Are those 10K resistors isothermal? You want to keep them the same temperature, I think.
It's not critical.
Even at 0.01, you can afford a little temperature?
These are very low temp coats. They're 1 part per million per degree C. So if they're off by a degree C, nobody cares.
So you don't have to mount them on a block or do any of that nonsense. Okay.
And I put in a 0.01 mic filter to keep the noise out. Now, talking about this circuit, eventually we'll talk about what's better than this, but why did I put in this 100K? Well, if a megohm would make it start, then 100K should make it start with a good safety factor. So I like to have a good safety factor, but 100K, if this 18 volts changes by 10 volts, like 28 volts, you're going to have another 100 microamperes through here. This won't be a constant current. This looks like a stupid constant current source because it ain't constant except for one thing. Every time you change this 10 volts and this current increases by 100 microamperes, this transistor decreases by 99 microamperes, and the whole thing is extremely well regulated, so this works quite well.
And so how much change can you have here and still stay in regulation?
Oh, it's designed to roughly, from 11 volts to 28 volts.
Oh, wow, that's great.
Yeah. Now, what's better than this? Well, maybe, in some cases, an op-amp is better than this because an op-amp makes a precision current reflector. And again, this is well regulated. Now, is an op-amp cheaper than 4 transistors? Yes, some op-amps are cheaper than 4 transistors. Are they smaller than 4 transistors? Yes, many op-amps are smaller than 4 transistors. Is it better than 4 transistors? Well, DC it probably is. But at AC, at a megahertz, who knows? I don't know. You have to engineer that. But this is an alternate way of making a precision current source with 1.4 milliampere through here. And it's pretty small, pretty good. You got all the questions on this already. Mm-hmm. Now we're going to talk about the output stage. We're going to take that 2-volt output and put it over here. Did I build this? No, I didn't build this. We got 2 volts and 2 ohms, heat sink, putting out an ampere into a load. Did I build that? No. What did I build?
The same 18 volts is up here?
Same 18 volts.
This is the 18 right here?
Yes.
Okay.
First of all, we did use Kelvin connections on the resistor. We got source and sense and force on the 2.1 ohms. Why 2.1 ohms? Because I had 2.1 ohms. It was a beautiful set of resistors, so we changed the voltage from 2.0 to 2.1. 2.1, it matches. We kept the op-amp the same. R and C makes a little filter, and now we have a Charlington. It's a triple transistor like a Darlington, only there's 1.5 Darlingtons. Again, we have a big heat fin. I got a TIP32 from Halted next door, and I got some 23906s to provide several milliamperes. Each of these transistors has some ohms in its base, ohms, so to keep it from oscillating excessively.
3 transistors, why is it Charlington?
Charlington.
With a T,
And we wanted to have a beta above 1 million, and we got a beta above 1 million. That's why we're using not just a Darlington. We also put 6.8K here and 68K here. So if this starts to leak at high temperatures, or if this voltage is moving up and down too fast, these transistors won't turn off and do anything stupid.
I had a question, Bob. I don't know if they can see it on the web, but there's a hole cut through the clear slide right here, and it's missing a place where like a knife is cut a hole out there.
I snipped that open because there was, cut it out, Paul! Because I drew this thing up beautifully and I had 2.1K ohms, and I said, I could redraw that, and if I redraw it, I make another mistake, so let me just snip it out.
ECO approved, all right.
Analog editing.
Analog editing.
PowerPoint can't do that.
Now, 1K, you can put a blank over, put your thumb over it. Anyhow, I put in 1K here. What the heck is the point of putting in 1K? That's not going to cause anything interesting, is it? And the answer is, if I have an ampere here, and if I have a microampere here, the microampere will cause a millivolt. I can measure this with a DVM floating up in the air. And if that's a millivolt, we know we have a beta of 1 million. And it was about 1/3 of a millivolt, so it means the beta was about 3 million. So that proves that the beta is high enough and not going to give us any trouble.
There's a cute little servo system, huh?
Yep,
You're
it's
comparing
current
the reference voltage to this voltage with
and
this.
if that's so, this has to be an ampere, and this has to be an ampere.
And everything's happy. This is great.
Now, what else did I add? I added in a 2-ohm resistor, and then I put a shunt across it, a wire shunt. What's that for? Well, when the wire shunt is there, you have a lot of output compliance, output swing. But if I open up the wire, This is a volt, and this becomes 3 volts, so you make a 2 volt change. Now, does the current change? Well, I can measure the IR drop right here. I can put the digital voltmeter, 6 digits, on my 1 ohm load resistor, and if I change this from 2 ohms to short circuit, and this doesn't change, that says we have good regulation. And the regulation is, 3 or 4 parts per million per volt, so it's very well regulated. Next thing, what did I add? I added 0.68 ohms and 0.68 microfarads to ground. What the heck is that one doing? Well, I looked at this and I said, as I was building it, you know, that 1 ohm is wire wound, it's going to be inductive, it's going to oscillate, it's going to ring excessively. If it's going to oscillate, I'm going to build this in and connect this in on the bottom end, and if I need it, I'll touch it in instantly and it'll stop oscillating. So I applied the power and it started to oscillate at a few dozen kilohertz, and I plopped this in and it stopped oscillating. So I tack soldered it and we're all set, except for the 1,000 microfarads. And of course, this power supply at 18 volts has a lot of current drawn from it, and the power supply I had was real lousy. So instead of replacing the power supply, I just slapped in 1,000 microfarads, and sure enough, it's well behaved. So this now makes a precision 1 amp current source.
That's great. Now tell me, you said that the reference part, the thing that makes the 2.1 volts, is good from about 11 to, what did you say, 27?
Oh, yeah.
Will this part also comply?
Yes.
You're kidding.
In particular, this will run about 30 volts, 32 volts, but the main point is, if this runs at 32 and this runs at 31 and this runs at 1 volt, that means this will also run when this is at minus 10. And this circuit will have to work when this is driven to minus 10, when the output load is driven negative. So this output can swing positive and negative.
It's still going to stuff the current.
And it's still going to provide a precise output current without much loss of regulation.
Now, if you put your hand on the knob of the power supply and change it, that's one thing. But what if it's a 60 hertz ripple? What if it's moving a little fast?
This is going to be moving.
Will it still maintain that constant current if there's a big 60 cycle ripple on this?
Well, we don't normally put a 60 hertz ripple up here, but I can put a transformer in here instead of this, and this will go up and down and up and down and up and down, and this won't change because the current is very well regulated, has high output impedance and high regulation.
And what are those heat fins doing over there? I see.
Let's keep it cool. We'll show you that in a minute.
Is that why it's red?
All these guys are going to be hot,
All
yes.
right. Don't touch that, Paul.
No.
All right. It's hot.
So you already asked all the damn questions, so I'm not going to tell you, do you have any questions? We'll just explain how well did it work. About 5 parts per million per volt of the supply voltage. That's because the heater may change. 4 parts per million per volt of the load. The alpha of the Charlington is in the vicinity of 999,996 or a beta of 3 million. And the power supply will run pretty good from 10 volts to 25 volts.
Wow. That's good
Now,
stuff.
we got pictures of this. We got the LM399 with its heater, with a little polysulfone heat shield. And the yellow guys are the voltage divider resistors, 0.01% precision wire wound 10K resistors. And this is the op amp and big ground plane feeding into the Charlington, which is on a heat sink. And this heat sink is indeed about yay big, because it is big and it gets very warm. And at 18 volt supply, it's running about 16 volts. It is getting very warm.
So that's this guy here.
That's big. That gets warm. Whereas the other guys don't get very warm. We'll cover that in a minute. But this definitely gets warm, and if you get to 28 volts, it's starting to get hot. We can put a fan on this. It's not critical because the alpha is very high no matter what. Adjacent to this is the precision wire wound resistor, which is 7 times 0.3 ohms at about 0.5%, and it's fairly low TempCo, and it's on a smaller heat fin, and it doesn't even get warm because it's only running at 2 watts, so it's not very much of a big deal.
And they're low TempCo resistors anyway.
And they're fairly low TempCo. They're not wonderful, but they're pretty good. And this is the overall view showing the main frame and the yellow wire wounds and the op amp and the 4 transistors in the current source and the 1,000 microfarads and the Charlington and the precision resistors. And here is the load resistor. The load resistor is only running about 1 watt, so I didn't bolt it to a real heat fin. I just strapped it to some copper clad, and it's going to be fine. And this is where we shove current into the load. So this worked extremely well. We're going to use this for some experiments that we'll discuss in a minute. Now, what's wrong with these circuits? Hey, they work. Well, yeah, but what's a modern way? Do we want to sell obsolete parts? Yeah. But would we rather sell modern parts? Sure, we like to sell modern parts. So can't we just slap some modern band gap references and a modern op-amp into that circuit.
You are the czar of band gaps, aren't you?
Yeah, but you can't put modern circuits in there because they run on different voltages. They like to run on negative voltages, not positive. They like to have a negative 18-volt rail, so we're going to turn that around. Furthermore,
there's another hole there. Was there a little short
there was a short there. We opened up
you
that.
Just snipped that little
we
thing
snipped
and-
that out, yes.
Oh, this is great.
So we're going to use a modern op-amp, the LMV2011, but it runs on a 5-volt supply. So we're going to take an ordinary cheap LM341, and it can run on the 18 volts, and it'll provide 5 volts output to this circuit and also to the band gap reference, the LM4140, which it likes 5 volts, and it puts out 2.048 volts with tight precision. Now this op-amp will then drive up to the base of an NPN Charlington. No, we decided we would try an IRF 511. And the reason for that one is to show a modern device. Now, this is a modern device. That means it must have less capacitance than a Charlington.
I don't think so.
No, I don't think so. A Charlington has 3 picofarads. This thing has 100, 150, 200 picofarads. Will this circuit tolerate that? I think so, but we're going to probably add an RC damper to make sure the LMV2011 doesn't mind the capacitive.
You're talking about that Miller capacitance.
Oh,
It goes
yeah.
from here, not just a gate source capacitance that everybody, that's thousands
Correct.
of picofarads on a big device.
Yeah, well, this one is bootstrapped, so every time this moves, so the capacitance input is not too bad, but this capacitance is direct.
And so anything moving up here is going to come and interfere
Yeah.
with your servo action.
So we're still going to need an RC damper up here. We're going to use the same ZL. We're going to use the same 2.1 ohms. And this will probably work quite well. This op-amp has better offset voltage, 4 microvolts typical.
Wow.
This has 0.1% typical. It doesn't need much trim range. So we really do like to help you guys out designing your analog circuits. Just remember, in theory, there's no difference between theory and practice. But in practice, there usually is quite a bit of difference. Now, we're going to dig out another set of foils before we come back and talk about what this circuit is going to be doing. And if I ask any questions like, Bob, why do you need one of these things? The answer is, there's a real application where you want to do it. Now, as I was saying, I like to measure things, and I like to use a circuit like this to do the measuring. And the application for this 1 amp supply really does need an 18-volt raw power supply, and we need the 1 amp output to swing into plus or minus 15 volts of compliance at about 60 cycles per second, or as we say on the continent, 50 cycles per second. It's called a Sealy box.
Sealy box.
And this goes back to the 1930s and 1940s, where engineers wanted to know, how hot is this winding getting in this motor? Or if it's a transformer, the same question, how hot is the transformer getting? Well, the way to do it is to allow for the fact that the winding is made of copper at about 3,700 parts per million per degree C. Okay, so we run this thing and we get the motor good and hot under full rated conditions, and then we turn off the power and we connect the winding as soon as it's safe over to a precision Wheatstone bridge. We turn all the knobs, and we get a precision reading of the copper. So if this was 10 milliohms, it goes up 10, 11, 12, 13, 14 milliohms. You can measure that.
Of course, the motor would have to stop, right? If it's spinning, it's going to generate voltage.
It might
so
just generate. So sometimes it's inconvenient to actually turn the motor off. And if it takes any time to take the readings, the copper is going to cool off. Therefore, it's going to really hurt your accuracy. So Dr. Sealy's solution in 1955 was you read the ohms of the copper while the motor is running. It's like measuring the spark plug gap on your engine while the motor is running. Well, he can do it because he knew how to do it. Now, Mr. Sealy did not have a precision current source. He did not have a precision DVM. But that's the modern way. So let's use a modern approach. How hot does this winding get? Well, we're going to use an isolation transformer as a bucking transformer. Now let's stand here. We're going to apply 110 volts AC or 220 or whatever it takes. And sure enough, there's 100 volts up here. And there's 100 volts here coming down, and there's 100 volts here coming down. So this voltage is nearly ground. It might be off by a few volts. It'll be off in quadrature, but if we put a big capacitor here, there's not going to be much voltage. How big a capacitor do we need? We need at least 1,000 microfarads per ampere. So for 10 amperes for a 1-horse motor, you're going to need 10,000 microfarads rated at a couple hundred volts, which gets to be big and big and big, a whole batch of big capacitors. But all they have to do is not leak. We're going to shove our current source through one set of windings through the motor into ground.
So that's the only DC path.
It's the only DC path.
There. See another little edit right there?
That's an edit, correct.
This is great.
Now, we look at the voltage here. How big is the voltage? Well, we shove an ampere through 20 milliohms, you'd have 20 millivolts DC, plus a little bit of IR drop. You have to subtract out the resistance of the transformer and subtract out the resistance of the wiring, but then you can tell what's going on here and how warm is this getting. So if this was 20 millivolts DC at room temp and 24 millivolts at 85, you'd say, it's not 125, but it's warm. It's very warm. Might be 75, 85 degrees C. All we have to do is separate out the AC. Now this could be 4 volts AC. It could be 6 volts peak, 12 volts peak to peak. We don't care because we're going to tolerate that when we're driving the 1 ampere. The 1 ampere will flow no matter what. And the AC voltage will get filtered out. So we're going to show you in a second a filter and a DC amplifier which will feed to a digital voltmeter. Any other questions while we're on this page? In concept, we could use a low-pass filter, but I prefer to use a notch filter. This is a basic notch filter, and if you ground this point, it's got a vicious Q of 1/3. It's got terrible notching. But if you simply connect this voltage to 99% of V out, the Q goes up to 5 or 10. You can trim this pot to get a Q of 5 or 10 or 20 if you need it. And the DC comes right through here and comes to your DVM. This has no effect on the DC voltage. It only notches it out. So you can get 60 or 70 hertz, 70 dB of rejection at 50 or 60 hertz as required. You put in your 4 volts, you come out with 4 millivolts AC plus 20 millivolts DC. This will not goof up the digital voltmeters. You can easily read the DC. And as the part warms up, the digital voltmeter says, ooh, it's increasing. This voltage goes up and then flattens out until it's not going to increase anymore because it's warmed up as much as it wants to do.
Guitar players love those notch filters because it takes the hum out of their Stratocaster.
Yeah.
Now, this is a precision amp also? You'd want a precision amp
This would be
there?
a precision. You
Like
don't
our
want
2011.
Overkill? It might do it. You have to make sure that it will tolerate the 4 volts AC over here. It might work, yes. I was thinking of the LF411 because it doesn't care.
Yes.
But the 2011 would work because your offset voltage would then be negligible. Now, what am I going to do with this thing? I'm going to run a motor. I'm going to run a centrifugal start motor where the centrifugal start switch provides a lot of current through the start winding as it's starting. And then as soon as it turns over fast enough, this switch pops open. There's no current in the start winding. The run winding does all the work, and it does its job, and it runs either at no load and it warms up a little, or at full load and it warms up a lot, and it's a motor. I'm going to put the Sealy box in here. I'm going to put the Sealy box in here to measure the resistance of this. Okay. And my proposal is that if I add 20 microfarads across the centrifugal start switch, it's going to run current through here. That sounds stupid. Running current through the start winding, it turns out it will act a little bit like a 3-phase motor. This current will provide improved torque and, I believe, improved efficiency. I'm going to have a watt meter in here, and I'm going to show that the watts is decreased for the same amount of load. And the self-heating is decreased. The resistors will heat up less. This resistor, this path of the start winding will get less hot than it had if it had no current through it. So that's the theory, and I got to get this thing running. That's why we're building this thing up to tell, is this getting warm or is it getting hot? So we really do like to help you guys with your analog applications. Thank you very much, and remember, my favorite programming language is solder.
No spice for you, huh?
No spice for me. The other day they said, Bob, do you like to turn the spice off after your simulation? I said, no, I prefer to turn it off before the simulation.
Then it won't lie to you.
Then it won't lie to me. That's correct. Now, we're going to have a sponsor who has a real live person.
Yes.
And would you like to introduce him, Paul?
Okay, as we said, OK International and MetCow is our sponsor. Today we have Paul Wood from MetCow who's going to talk to us about how do you prototype. When Bob and I were on the analog seminar.
Is your favorite programming language solder?
There he is.
Hi, Paul.
Hey, Paul, how you been?
Hi, Paul.
So we're going to talk about some of these terrible, terrible problems that engineers kept asking me about. How do I prototype with these tiny packages? We have one right here. I don't know if a camera can get in on it. It's on the tip of my thumb there. If you can see, that's one of our tiny little micro SMD packages.
Don't sneeze.
Don't breathe. I'll have a story about the first time I tried to use one of these. How do you put that on? Here's a little part, a sequence showing how we've moved smaller and smaller. It used to be little tiny leads that you could get at with the great Metcal soldering iron that Paul Wood makes. Now it's getting smaller and smaller till finally there's no more pins. It's an LLP package. And Metcal has championed, they've just pioneered how to deal with these, how to mount them, how to unmount them reliably. And Paul's going to talk about some of the exciting stuff they've got for us.
Well, you're using one in your lab, which we're going to see that you've done, and you try and prototype it with a soldering iron and solder. And you can prototype this and you can get things working satisfactory sometimes, but as they get more complicated and they get more leads, you know, it gets more difficult. So we made some stencils that allow us to mount these the same as a production with solder paste and with placing it with vision. So we have a stencil here.
And this is what puts the solder paste on the part.
Right.
You don't, because some people were used to putting it in production. A lot of times they'll have a stencil for the whole circuit board,
Right.
this big expensive thing.
So we take this one part that you want to put on, we mount it in the stencil, we turn it over, and we screen print with solder paste on here a amount of solder paste equally on all of the pads, on the ground plane, and then a machine picks it out of here, which you can see on the national website where to view this being done automatically.
We should have it up on the pane. It should be right next to us now on our...
Align it, place it, and solder it. So it's done by an operator on a rework machine. It's not done with the soldering iron, with tweezers manually. And that's the preferred way for when you start getting more aggressive in the size of the I/O and the difficulty involved in doing it. Mm-hmm. And the Metcal iron you use in your lab, which we'll see, and how you can prototype it that way.
Right.
But this is the rework of a board where you want to test reliability, you want it to be high quality, and perform the way you want it to perform.
Right, and with these packages, it's just essential that you have a hot air rework station and Metcal soldering irons just to do touch-up and things like that. Shall we go over to the lab now? We're going to move the cameras over. We got a big setup today over in the lab. We got all kinds of good stuff to show you. So we're going to shut the cameras down, get them all repositioned, and start them up again, and kind of show you how we prototype things here, the history of prototyping. We have one of Bob's, I call them airball. They're not air balls.
Rat's nest.
They're a rat's nest, which I'm used to laying out circuit boards. Rat's nests are part of a circuit board concept. So air balls are rat's nest by another name. We have all this good stuff to show you, so let's go see what we have in our lab now. Okay, welcome back. We're over on our lab segment now. When Bob and I were doing the analog seminar, whether it was Atlanta, Georgia, or Vienna, or any other city in the world, engineers kept coming to us and asking over and over, how do I prototype with these tiny little parts you make now? How can I deal with these small, infinitesimally small parts, some of which don't even have pins? So we're going to go and show you, we've got our beautiful bench set up here. We're going to show you the evolution of prototyping and what you have to do today to get a successful prototype into manufacturing. Now over here we have, I call it an air ball. Bob doesn't like that. He says it's a rat's nest. Bob, what circuit is this? What
Well, that's
part?
the LM331, voltage to frequency converter.
I see.
Yeah.
This up here was the reference section, you said?
Yeah, reference section.
Okay, and all these transistors, all of this is an integrated circuit. This is the way Bob started making an integrated circuit. It's air wired, it's very fast. You could see when Bob did the current source. His stuff is just built with discrete components, wired in the air. That helps you in a lot of cases. It takes stray capacitance away. It can remove various inductances, things like that. You can tune it by how you solder the board together. But then there are limitations to it. If you want a very fast circuit, that can cause a problem. If you want low leakages, well, air is good. You can see the femtoamp circuit that we did was low leakage. But here, you see the next stage. Here are a couple boards where we just took plain copper clad, single-sided here, double-sided, and carved on it with an X-Acto knife, and actually carved the traces in and built, you can see Paul's an expert at this, Paul Grohe, building these little structures, making little boxes. You can see that in our femtoamp meter. John Bittner built this board. He's a resident guru we have, went over to power on us. The next step, okay, so now you've carved up, you can see it still dips, things like that. Here's one of the milling machine boards. Several companies make milling machines. And here you can see the milling, you do a normal board layout with a OrCAD, ProTel, you name it. We use Cadence sometimes. And the milling machine carves the traces in. And so now you've got a circuit board with controlled width traces. That can be good for controlled impedance. You can do something on the bottom. The big disadvantage, no vias. So you've got to solder in the vias or pay a lot of money for a via machine that you can't use because the health and safety people get upset. Now you've got those tiny, tiny parts. What are you going to do? We want to tell you about these little conversion boards. These, I think, are DigiKey has them. Several companies have them. Paul, what do you got? You've got a couple of those over.
Yeah, these are the little conversion boards by both Aries and Capital Technologies. This is Aries Adapta-Chip, the little green ones. This is an 8-pin SOIC to dip board. And this is the TSSOP to dip. They just go pin for pin, 1-to-1 pins. And then these are the Capital surf boards. And here, this is an this is a SOT23 to SIP adapter board. And this one over here is a SC70 to SIP adapter board. Just brings the pins out 1-to-1, and these allow you to insert them into the solderless breadboards or into dip sockets so that you can wire to them conventionally.
Now the headache with these is high-speed stuff. You're going to be in trouble, right?
These are good. We use these for frequencies up to about 50 megahertz. After that, the lead inductance and the capacitance does come into play. But for low frequency stuff, for low power stuff, they're fine.
Okay. When you get the parts small enough and you need to get an entire circuit built, you're going to run out of just cutting stuff with a milling machine. You're going to have to do something else. That's when you have to do a complete board design. And you get, I like to use OrCAD. There's many packages. You draw the schematic. The schematic helps you do the layout, and you make a real circuit board. And you use one of the prototyping houses. There's Proto Express here in Silicon Valley. PC Pool in Europe is getting a lot of attention. Advanced Circuits in Colorado is used quite a bit. Look in the back of the magazines, read publications. There's a ton of publications in the back ads, all these different circuit board houses that do quick prototypes. The beautiful thing, the reason I like the one here in town, Proto Express, this board is a 4-layer board. It's about 8 by 11 inches. You can get 2 of these for $51 because it's 4-layer. You can get 2 of those in 4 days. So that's unheard of. You shouldn't spend so much time worrying about the circuit board. Just spin it, try it, and if you need to make changes, spin it over again. Here you can see you get an assembly drawing, you can hand this to your assemblers, they can build it for you, and you're getting into a more controlled environment. You're getting it to a place where it can go into production quicker. You're in a controlled situation, which you'll see why the Metcal is so important. Now, I wanted to bring out 2 of the things about prototyping with this tiny stuff. I learned, I have a bunch of machinist friends. The machinist taught me you have to hold things. So one of the headaches you have with prototyping is you've got to hold stuff. So you get your pan of ice. The pan of ice, this one has the standard jaws. They make Teflon jaws. Go buy the Teflon jaws because then you can solder right up there and it doesn't melt big divots in it. It's worth it. Here's something I stole from Paul's area that he didn't know about, but I'm sorry, I'll put it back, I promise. This is just one of these little gizmo things that you can hold a piece of solder here. It's got a magnifying glass, which is the other half of the equation. Once you hold it, here's a custom fixture made for one of our customers, for Sanyo. This is the power unit, the OPU, the optical power unit, used in a DVD recorder. Our part mounts right here. This whole fixture, this expensive milling machine fixture, was made just to mount this, so you can not only take optical measurements here, but it gives you a nice stable base that you can use to do rework. Now here's a evaluation demo board we made, and I did a bad thing. Paul Wood's going to yell at me. I used a hot air gun and tried to mount the part because it was a big, big rush. I didn't use a Metcal hot air rework station. And you can see, Paul critiqued this. This is an Xray. This is some of the other equipment you're going to need to do small, tiny packages and LLPs. So here's an Xray of this part on the board. Excuse me, Paul. This is a similar board. You can kind of see, this is the part right there. You can see how small it is. It's an LLP part. There are no pins exposed. So you use this X-ray to kind of see through the part to see if there's any solder shorts.
And was this functional? Did this work?
No, it didn't. We have an open on it.
You're going to try and fix it, though?
We're going to try with your Metcal soldering station to fix my mistake.
Well, once you get it working, and you got it working in a lab environment, I mean, that's the point of your trial here. But if you want to do high power or high reliability trials, this area here is solder, and this whole area should be covered with solder to take the temperature away from the body into the board so the component doesn't get hot.
You can see these big holes here are 9 vias that I put that's taking the heat down to the bottom of the board, so it's getting to ground planes and thermal planes where the heat can come out of the board.
So when we use the stencil that we showed earlier to print solder paste, you'll get a coverage totally across this ground plane, which will help you keep the component level and get the right temperature coefficient across the part when you're doing tests and reliability tests. So to do it properly, you really need to use a larger rework system to do this. But in the prototype environment, you're going to try and solder one of these to try and get it to work.
Right.
Because the component's rocking at the moment.
Yes, it's floating, exactly.
It's not level.
And this is another sin I committed. This is a no pullback package, so the pins go all the way to the edge of the black plastic. That's why I might be able to fix this. I didn't use the correct stencil. I didn't call Paul and say, hey, I need to order a stencil so I have the proper. Applying the paste is just as important as having that camera and prism system. It's extremely a controlled environment that Metcal gives you, and that's why you need that. Now, I got more props here, stuff, you got to see this stuff. I'm getting too old to use my natural eyesight. Here you can see this demo board, and I have my little, up on the scope here, you can see this is DC down here, this first division, and you can see there's an AC signal, a couple hundred, it's programmed here on our LaCroix, 354, oops, we'll take the touchscreen and turn it off so that doesn't happen, 350 some megahertz, that's this sine wave. We're measuring the mean, it's about 58 millivolts up here. Now that is the second channel. I'll flip a little switch and you can see, wow, it went down to 0. That shouldn't be. I've got a read channel enabled. This is a laser driver chip. What's happened is, this is the X-ray for this particular board. There's an open, this pin right here. Looks okay, but there's an open there. Now, Paul Wood's company also makes inspection systems that you can get down sideways and look underneath the part. And it's astonishing how much room there is under there, and you can see if the solder ball is touching. But because of my poor construction techniques, here's the way I figured out I had an open. It's dead, I checked the supplies, I checked the voltage, I'm scratching my head, I tried everything I could think of, and then said, oh, it's a no pullback LLP package. I'll take this scribe in here, and I'll run it along there, see? Now if you're looking up on the scope, it's kind of hopping a bit, but the scribe has shorted the pad on the LLP package that comes out to the edge on our no pullback style to the pad on the circuit board. Take it off. Oh, that's my problem. Now let's see, quick and dirty. This is live television, folks. We're going to see if we can fix this. Because I didn't use the Metcal hot air rework station, I got into this trouble. Let's see why it's so nice using these completed boards. They're durable, they're easy to use. So we'll get this. We got some prototyping, 10 thousandths thick solder. Look at this. See, this is why we love Metcals. They heat up instantly. You tend to turn them off because you don't leave them on all night. They heat up so quick. Okay, so let's see if we can get in there. This is not the sharpest tip they make, but let's see if we can Just rub a little solder. And by combining the microscope with the light, I can see it. Let's see real quick here. So, ground for the LVDS driver. We're monitoring the current with this one. I need this pin. I started designing banana jacks right in the demo boards because it makes it so much easier. Don't mix power and ground, not when the cameras are rolling. Okay, we're drawing 145 milliamps. Where's that SMA connector? Right here. Look at that. See, we've repaired the open from my bad construction, and now I can control it. I fixed that open with the Metcal soldering iron. You've got to have this kind of equipment if you want to successfully prototype modern parts. We've got the circuit up now, and we can see that it's oscillating. The DC bias is in like it's supposed to be. That's why we love Metcals. It can fix screw-ups that I make earlier. Another thing we love about Metcals is these Talon tweezers. These guys, for whether you're pulling, like Paul was talking about, you're pulling the surface mount component, they make some that are wide, and you can pull an entire IC off. But if you're prototyping a board and you're trying to use various different components, what you can do, you get the tweezers here. We're going to take a little capacitor we have. You just set it down there. Off it comes. Right there. Isn't that great? And you can set that down, go find a different value component, and if you're more coordinated and less nervous than me, you can set it right where the other one was, let it heat, and if you're just right, you can pull it off, and you can just try different values very quickly.
And you won't damage them because the temperature control is within a couple of degrees at the tip, because this is a RF iron. This is not a ceramic heater where the temperature is high at the tip. So this is controlled regardless of load on the board. And so the temperature in our catalogue is the temperature at the tip, and it never rises or falls.
No
sharply.
calibration. It's very dependable.
You will not, damage the chip with high temperatures.
They have radio frequency coming up the cable. Then the inside of these removable tips is plated with a material. The Curie point of that changes. And that's how it servos and controls the temperature, controls it so tightly you don't need to calibrate anything. And that's why they heat up so fast. That's why we love them. We don't have to, Metcal didn't ask us to promote their stuff. We asked them to please come on the show so we could tell you how good their products are. So that's a great success we had, live television at its best. Bob, is anything else you'd like to add?
I can't think of anything else. That was a very good lab segment. Thank you, Paul Rako. Thank you, Paul Wood.
Thank you.
Thank you, Paul Grohe. Friends, thank you very much. I hope you learned something too. We had a lot of fun and we learned something too. Bye-bye.
Bye now.